So if I share my screen, I guess you can see the lecture notes on there. Last week we looked at this topic of stress systems, and we went through this tutorial here. And we did questions 2 and 3 on that tutorial, and it was sort of really covering Poisson's ratio. I also said last week, I'm not much of a fan of question 1 on that tutorial. I think it's not really indicative of other things that happen in the module. It sort of jumps right in at the deep end with a very complicated question that doesn't have a lot to do with the core topics in this solid mechanics module. So although we may come back and look at question 1, I'd encourage you to spend much more time looking at questions 2 and 3. And then question 4 is kind of its own thing as well, but it's an interesting question and one that you might want to think about. It's kind of applied in a funny way. And then I guess there are some lecture notes associated with that and maybe a lecture video as well. The next topic is axial loaded members. And again, there are some tutorial questions and there's a lecture there. And that's really what I think I'm going to go through today, is this tutorial sheet here. And here I'll probably start at question 1 and then we'll just see where we get to. So that's my thinking on what would be good for today, but I'm just going to bring it back and stop screen for a second and just ask if anyone has any anything they want to input on that or to ask about that. One of the things that I know Rakat was asking about the start of this tutorial, and that I think is really important in the solid mechanics module, is just to get a feeling for how the topics divide up. And at the start, it kind of feels like everything blurs into one. But starting about next week, I'm just going to try and get my system back. So starting soon, I hope you'll find, Moodle's just gone a bit slow for me, but I think I can remember there'll be maybe a week on bending, a week on torsion, a week on combined stressors, and it'll start to make sense that there are kind of individual topics that you can practice on their own that build up to this module. So that becomes clearer when you've done them and you look backwards and you think, all right, that's a bending question, that's a torsion question, that's a stress transformation question. But if at the moment it feels a bit like everything's blurring together, I would say hold on a couple of weeks and then I hope it'll start to become a bit clearer. Any other questions before I start? Okay. I'm not sure quite how well this screen sharing is going to work, but let's try it and see. Just give me a second to try and get my camera up and running. It worked fine when I practiced it earlier, but that's never a guarantee it's going to work now. This may also cause my webcam to stop working, but as I say, that's fine. I'm just going to turn my webcam off to see if that helps. And for my final trick, so can I check, can you see the axial loading problems over here on the left-hand side and a video of my blank sheet of paper and pens on the right-hand side?
Yes.
Great. Okay,
Yep.
let's take it from there and see how we get on. Again, just I think I can keep an eye, I've got two screens, I can keep an eye on the chat window, and obviously you're welcome to just turn your microphones on and shout out if there's anything that you think I need to cover more or better or differently. Weird. That looks good. So we're going to look at question 1 here. I think you all know me well enough to know that I'm going to start by drawing a diagram. Just get this cable out of the way. That's a good setup. So in question 1, we've got some kind of a round bar. I might just even try and draw this vaguely three-dimensionally, just so I remember that it's round. But the important thing is, can I draw that bit? Not really. That it looks something like that. It's 0.25 meters in length, in total length. These sections here are, I'll put it on there, 50 millimeters in diameter. And there's a tensile load. So these are the kind of wordings to get used to early. A tensile load means it's in tension, which means it's pulling outwards, and that's 150 kilonewtons, like so. And the other information that we want within the question is, first of all, we're told Young's modulus E equals 206 gigapascals. And then the question, the stress in the middle of the bar is to be 215 megapascals. We'll call that part A, maybe. So the stress in the middle should be 215 megapascals. This is really another one of those stress-strain type questions that in theory, I think we could have solved last year based on the stress-strain work we did in first year. So the important thing to note, first of all, is stress is force over area. And therefore, I guess I can say 215 times 10 to the 6 is 150 times 10 to the 3. The force, you might be happy just saying by observation the tensile stress anywhere in this bar is 150 kilonewtons. If you want to kind of use a rigorous approach, you could think about the method of sections, that if we made an imaginary cut somewhere in the middle of the bar, we'd have a force of 150 kilonewtons pulling to the right on our section, and so we'd need 150 kilonewtons pulling to the left to balance that, and that means there must be an internal tension of 150 kilonewtons. So again, I don't think you have to justify that. I think you can just write it down, but it can be justified if we need to. And then the area is going to be pi r squared. And rearranging that, I suddenly realized I don't have a calculator. So I'm just going to run and get one. I'll be back in 30 seconds, but I'd recommend everyone have a go at calculating it, and we'll see if we get to the same answer. Okay. If we rearrange, we'll be able to say pi r squared is 150 times 10 to the 3 divided by 215 times 10 to the 6, and therefore r equals the square root of 150 times 10 to the 3 divided by pi times 215 times 10 to the 6. And that's now something I can put into my calculator. So I'll do that. 150 times 10 to the 3 divided by pi divided by 215 times 10 to the 6, and then square root of that, which comes out as 0.0149 meters. And I guess I can then say, just to finish off, the diameter is 2 times the radius, and that's going to be 0.0298 meters, i.e. 29.8 millimeters. And I think I can just move that up a touch so you can all just see that final answer. And that's my final answer for the diameter of the middle section. And the good news is it matches the answer we were expecting from over here. So it's all the usual things at the moment: drawing a good diagram, making sure you've got a good understanding of what's being asked in the question, and then using these stress-strain relationships to get towards an answer, working through the maths, making sure we're on top of the calculator skills. You know, this is the kind of thing where you can easily make a mistake in just how you put it into your calculator, and then eventually getting to an answer. And I suppose the last thing that I had to be careful of is I calculated a radius here, and I just have to remember that the question asked for a diameter. And in this entire module, I would say the most common mistake that people make, and definitely the most common mistake that I make when I'm working through problems related to the module, is forgetting that sometimes we need to talk about radius and sometimes we need to talk about diameter, and we need to be able to jump between them. So just make a mental note or even a written note to always check, is it a radius or is it a diameter? Does that make sense?
Yes. Yes.
Great. Okay, let's move on and look at the second part. The total extension of the bar should be 0.2 millimeters. So this is like B, and what it's really saying, I guess, is delta L, the change in length, is 0.2 millimeters. And that's sort of two changes in length. That's delta L. I'm going to use a subscript 50 for the 50 millimeter diameter bits, and the plus delta L subscript 29.8 equals 0.2 millimeters, which is 2 times 10 to the minus 4 meters. It might just be worth at this stage drawing the diagram quickly again, because we might want to mark on a couple of other lengths. This time I'm just going to draw it pretty simply as a two-dimensional object, and we know that that length is 0.25 meters. This length here I'm going to call x. In a way, that's something that we don't know at the moment, which means that this length here is also x, and this length here must be 0.25 minus 2x, because these three lengths together have to add up to 0.25. So now we can start using our stress-strain relationships to work out what x must be. And in a way, you could say I've done this the wrong way around. The thing we actually want to know is the length of the middle section, but we've already written down an expression for that in terms of x, so we'll be able to get to it pretty quickly. Let's just write down again, stress is force over area. Strain is change in length divided by original length, and stress is Young's modulus times strain. And we're given a Young's modulus in the question, so we'll be able to work with that in the end. So, if this was equation 1, then I can rewrite equation 1 using this relationship here. Delta L must be epsilon multiplied by L. So I can say epsilon, the strain in the 50 millimeter diameter bit, multiplied by the length of the 50 millimeter diameter bit, plus the strain in the 29.8 diameter bit, multiplied by the length of the 29.8 diameter bit, is going to be 2 times 10 to the minus 4 meters. Now I can keep going with some substitutions. I know what I can do with epsilon. I can use this equation to say epsilon is stress, strain is stress divided by Young's modulus. And I also know that the length of the 50 millimeter bit is x here and x there. I'm going to treat those together and make it 2x. And the length of the 29.8 millimeter bit is 0.25 minus 2x. So stress in the 50 millimeter bit divided by Young's modulus multiplied by 2x, plus stress in the 29.8 millimeter bit divided by, stress in the 29.8 millimeter bit divided by Young's modulus multiplied by 0.25 minus 2x equals 2 times 10 to the minus 4. Now I can use stress is force over area, and I know all of the forces and all of the areas, so I can substitute in to leave x as the only unknown in this equation. So I'm going to leave everything algebraic for the time being. Force divided by pi times 0.025 squared multiplied by E, all multiplied by 2x, plus force divided by pi multiplied by 0.0149 squared multiplied by E, all multiplied by 0.25 minus 2x equals 2 times 10 to the minus 4. At this stage, first of all, it's just worth having a recap of what I did in that last line. all I've done is to substitute in stress is force over area, and I've used area equals pi r squared. So 0.025 is the 50 millimeters that were given in the question, divided by 2, because that's a diameter and I want a radius. The second thing that I'm going to do at this stage, I talked last week about how sooner or later it's easier to put everything into numbers. I think we've reached that point. So I know F is 150,000 and E is 215 times 10 to the minus 6. So I can put all of this into my calculator now and start getting some numbers out. So this comes out as 0.355 times 2x plus 1.000 multiplied by 0.25 minus 2x equals 2 times 10 to the minus 4. Let's keep going and see where we get to. I'm slightly worried that I may have made a mistake because I can't quite see how this is going to get me to the right answer, but we'll just try it and see. So this gives me 0.71x plus 0.25 minus 2x equals 2 times 10 to the minus 4. And if I now jump to the next page, I can rearrange, sorry, that last line should have been 0.71x. I can rearrange all of that to get 1.29x equals 0.25 minus 2 times 10 to the minus 4. And that's all in meters, and therefore x equals 0.194 meters, which is the wrong answer. So let's just go back and check.
I think I see the mistake.
Yeah, go for it, Ragat.
So the radius, it should be 0.125, not 0.025.
50 millimeters is 0.05 meters, I think. Is this right? So half of 0.05 is 0.025. Do you mean this number here? If you can see my mouse. I think that one's okay. Anyone else see my mistake? I kind of feel like it's somewhere in these 3 lines. This line seems okay to me. The total change in length has to be 2 times 10 to the minus 4 meters. I'm happy enough that the changes in length are the strain, which is a very small number, times the original length, which is a slightly bigger number. And so that seems fine. That seems okay. and that'll still come out with a small number in the end for the change in length. Strain is stress divided by Young's modulus. That's okay. I guess my feeling is these numbers here are somehow too big. Looks like the problem, because I kind of want what's on the left-hand side here to balance what's on the right-hand side. That force is correct. Rakat, why did you think this number should be a different number?
Because I thought you're trying to get to a radius.
Yeah, that's right. But I started with a diameter
divide
of 0.05, which is 50 millimeters. I guess the other thing we can do is just to look at the given answers and see if there's anything there that helps us. I know that's sometimes a frustrating one, but I don't want to spend too long trying to find my own mistake. So let's see if we can help ourselves out. So 29.8, that went fine. Let's just look at this working and see. I mean, to be honest, I think this is all quite good experience, and I've seen exactly where I've gone wrong, and it is going from this line to this line, and it's somewhere in between calculator work and paying attention to the problem. I was using 215 times 10 to the 6 for Young's modulus here, but of course that is the stress from part A. Young's modulus is 206 times 10 to the 9. So let's correct some numbers and see if we get to the right place. I'll go back to the question now. I think that's all okay. So 150 times 10 to the 3 divided by 206 times 10 to the 9 is more like what I want, divided by pi, divided by 0.025 squared. And this now comes out as 3.708 times 10 to the minus 4. And that's a more likely number because it sort of balances up with what's going on the right-hand side. That was where I was slightly aware that something was going wrong, because these numbers on the left-hand side were so big, they made that number irrelevant, and that seems like a problem. Okay, I'll do the next one. 150 times 10 to the 3 divided by 206 times 10 to the 9 divided by pi divided by 0.0149 squared. And that comes out as 1.044 times 10 to the minus 3. So this is 7.416 times 10 to the minus 4. And this is 2.61 times 10 to the minus 4, and this is 2.088 times 10 to the minus 3x. And all of that equals 2 times 10 to the minus 4. Good. Let me write out that line again. I'll get rid of that bit of paper. It's wrong. And then we can finally get to the answer on this question. And then we'll have a bit of a recap and think about what happened there. So 7.416 times 10 to the minus 4 times x plus 2.61 times 10 to the minus 4 minus 2.088 times 10 to the minus 3x equals 2 times 10 to the minus 4. Now what I want to be doing is getting all the x terms on one side and all the numbers on the other side. So let's get the x terms to be 2.088 times 10 to the minus 3x minus 7.416 times 10 to the minus 4x equals 2.61 times 10 to the minus 4 minus 2 times 10 to the minus 4. And that will let me get to an answer now. (1.3464) times 10 to the minus 3x equals 0.61 times 10 to the minus 4. X equals 0.045 meters. Because I've done everything right from the start in meters, I had all my areas and things in meters. I now know my answer is going to be in meters. And so we can finish up the question now by remembering what we were asked. If we just go back to this diagram, we now know x, but we want to find the length of the middle section. Which is 0.25 minus 2x, which is 0.25 minus 2 times 0.045, and that will be 0.16 meters, which is what's given in the question. So eventually we get to the right answer. Right. There are a few things to think about from having worked through that. The first is it looks like a fairly simple question. There's not a huge amount going on in the diagram, but you can see it had enough going on that I made a mistake and came to the wrong answer. Without wanting to justify my own mistake, I think sometimes it is useful to watch people make mistakes and then see what they make of them and how they go around and find what went wrong. So some of this is about developing an intuition for what kind of numbers are going to be right in any given place. And then the other thing is just to be absolutely careful about what numbers you're using at each step of the calculation, because my problem was I thought I was using Young's modulus, but I was actually using a different number from the question, and that led me to a wrong answer. The final thing to say about that question is it turned out to be quite a lot of work, right? We've got 3 sheets worth of working. That's about standard in this module. In first year, I would say most problems you can finish on 1 page. In second year, that's just not going to be the case. So one of the things that everyone needs to be building up is that familiarity with writing an answer that takes 3 or 4 pages to get to a final answer. And maybe, you know, I think when the exam comes around, you will have, I think 2 hours, but it might be 3 hours, and you'll be expected to do 5 questions. That's what it's been historically. So you can do the calculation. That's about 20 minutes per answer, and they take about 20 minutes to do. So we're not used to just writing for a long time, working through things methodically. That exam will be hard work mentally and even physically. Just the action of writing becomes hard. Any questions at this stage? Again, feel free to put them in the chat or to call them out loud. Okay, in that case, let's go on. Question 2. Having said most questions are about this length, I think question 2 is actually slightly shorter. Let's see if we can get it done in the rest of this class in the next 10 minutes or so. If not, we'll leave it as an exercise to be completed. So, question 2 has a steel strut of rectangular section. Can I draw a rectangular section strut? And it's again a sort of larger one supported by a slightly smaller one, something like that. There's an overall force of 100 kilonewtons compressing it, and we know some of the dimensions. This is 150 millimeters, which is 0.15 meters, from there to there. And from there to there is 100 millimeters, which is 0.1 meters. And this one is 40 millimeters by 50 millimeters. It won't really matter which dimension is which. And that's 0.04 meters by 0.05 meters. And this one is 0.025 meters by 0.025 meters. Good. So we've got most of the information we need, and Young's modulus is 220 gigapascals, which is 220 times 10 to the 9 pascals. And if I look like I'm about to use the wrong Young's modulus, shout at me. So in this question, we've got all the dimensions, and it wants to know the compression of the strut. So we can actually just do this in 2 parts. First of all, let's look at the 150 millimeter section. The stress, I guess we can start from, is force over area. Stress is Young's modulus times strain, so that must be force over area. And then that means strain is force over area times Young's modulus. Strain is delta x, the change in length, divided by the original length. And that equals force over area times Young's modulus. And so finally, what we can say is the change in length is going to be the force times the original length divided by the area times Young's modulus. And that is 100 kilonewtons, 100 times 10 to the 3, multiplied by the original length of 0.15, divided by the area, which is 0.04 times 0.05, and divided by multiplied on the bottom line by the Young's modulus, which is 220 times 10 to the 9. And that's all something I can put into my calculator. And I get 3.41 times 10 to the minus 5 meters. Then I can just go and use the advantage of having done things largely algebraically, so leaving things in letters till right at the end, is that now I can do something pretty quickly for the 100 millimeter section. I know that the algebra will be the same, and the change in length will be fx divided by AE, which in this case is 100 times 10 to the 3 multiplied by 0.1 and divided by 0.025 squared times 220 times 10 to the 9. and that is 7.27 times 10 to the minus 5 meters. I'll move on to a new sheet and finish this up. The total compression is the sum of those two. It's the compression in the 150 millimeter bit of the strut plus the compression in the 100 millimeter bit of the strut. So that's going to be 3.41 times 10 to the minus 5 plus 7.27 times 10 to the minus 5. And that comes out as 1.068. I'll call it 1.07 times 10 to the minus 4 meters, i.e. 0.107 millimeters, which is the answer that's given in question 2 there. So that one is slightly shorter, slightly easier, I think, than question 1. Maybe if you're making notes on this at the moment and you're going to come back to it for revision, make a note to start with question 2 because it's a better introduction, and then question 1 involves using the same ideas, but you have to be able to manipulate them a bit more. Okay, that's what I want to do for today. That's a good place to leave. You'll see that question 3 kind of looks like more of the same, only in question 3 there are 2 materials. There's some steel and there's some concrete, and I think I don't want to start on those ideas now about what we do when we've got multiple materials, because that's quite a big topic to think about, and I want to leave it for next week. So I'm going to stop sharing that screen, see if I can turn my camera back on, which I can, which is good, and just finish up by seeing if anyone's got any questions or anything that they want to raise from all of that we've done today.
Ben, are there any pages in the textbook?
Yeah, that's a good question. Annoyingly, I don't have my textbook with me at the moment, but maybe what I can do is to try and bring up the library copy. I'm just going to do this on my other screen. Okay. Sorry, I'm just searching for the textbook now, and I've got it. So we can share that screen. I hope you can see now my screen with the information about the textbook. I'll try and log in. To have a look at it. Okay, so it looks maybe like we could read this online now. Let's just try, see how it goes. Awesome. Once I log out, it looked like there are another 2 online copies that anyone can read right now, and once I log out, you'll be back up to 3. What we're really looking at is still this stuff here around tensile forces, compressive forces, stress, strain, and so on. What we nearly got to at the end of the question was this topic. Question 3 would have been on compound bars with multiple materials involved. So let's jump to page 48 or so. Let's see where we are. Page 48. That went well. I guess this is revision, really, this compressive force. I've seen that there are some example questions online about shear forces, so it might be worth looking at all of this, and then stress and strain are going to be covered in the next couple of topics. You know, this kind of problem here, problem 6, for example, is really exactly the kind of revision we want. It's like a simpler version of that question 1 through, so that might definitely be somewhere to look. And then by the time you get to something like question 9, you're looking at things that are quite similar to what's being covered in class at the moment, I think. So that's good and important. And then there are these practice exercises, and I think there are answers to them at the back of the book, but I can't quite remember. So all of this stuff I think is really good. And then I'm just going to jump forward through Hooke's law to have a look at compound bars. So this is what to revise just to get a bit ahead at the moment, I would say. Compound bars, it's what happens if you have multiple materials. And the key ideas are these. You need 2 different considerations. Equilibrium, which we've talked about, loads, so the forces have to be balanced. But you also need this new consideration, which is compatibility. And what we're saying there is, if you've got reinforced concrete with concrete and steel together, and you compress that concrete, the concrete and the steel compress by the same amount. You know, if you change the length of the whole thing and it's made up of 2 materials, you're changing the length of both materials equally. And that turns out to be powerful in the same way that equilibrium was powerful. We can start writing down equations. The change in length, delta x for the concrete, must equal delta x for the steel. And that means that we've got a new equation we can work with, and we can get some new information from it. So that's the kind of thing that's being covered in this section here, and it's the kind of thing we'll look at next week. And again, there are all these additional problems, and even these short answer questions are definitely worth making sure you're good at. So I would say all that section of the book is really good revision for what we're doing at the moment. And then it moves, at this stage, it moves on to something quite different. You might want to read about tensile testing just for interest, but it's not quite what we're talking about in class right now. So I would say pages 48 to 63, if you can get absolutely on top of everything in there, that's a really good place to be in this class at the moment. Does that help, Rakat?
Yeah, thank you.
Cool. Anyone else want to ask anything? I'm just going to make sure I sign out of this book so that it's immediately available for anyone who wants it. Good. That is signed out and all ready to go. Yeah, any other questions?
If someone's signed into a book for a while, does it kick them out?
I'm not sure. I sort of wonder that. It looks, when we looked at maybe last week or a couple of weeks ago, all the books were signed out online. That's a rush of enthusiasm from everyone in first year to go and look at them. But then as the semester moves on, I think you'll find they're more often available. I think it's always a courtesy with that kind of system, if you are not looking at it, just to try and remember to sign out. We all forget from time to time. I hope it'll automatically log you out after a while, but I'm not sure.
Is there a way to maybe download the book whilst you have access to it so you don't have to sign in?
I think you can download some chapters, but I would just have a look online and see what you can do. The library websites are usually pretty good. I've found, and it's clear what you can and can't do. Often with textbooks and things like that that are available online, you can download 2 chapters, and then if you want a 3rd chapter, you have to you know, do something different or read it online, because they don't want people to just share the whole book widely. But yeah, that's the kind of idea. And you know, obviously be careful with copyright issues, but for example, if there's something that you think is really useful in the textbook, you can always screenshot it or copy and paste the text just into a kind of revision file, and that can be a good idea to go with. Okay, I think that seems like a good place to leave things. I see Andrew left, he's had enough. So I'll stop there, and I will stop the recording. And if anyone wants to you know, ask any other questions or anything like that,